It can carve our landscape, yet so nurturing it can spawn life. We bottle its goodness, showcase its beauty, and seek its wonders at the far edge of our solar system. Now, water on Modern Marvels. Don't let this deceptively simple substance fool you. Beyond water's common veneer lies tantalizing complexity. Beneath the surface lurks a dynamic entity. Water radiates with the essence of life. Yet, it often unleashes its savage ability to destroy. Gushing from great heights, it packs the power to light up our cities. Trickling as a single drop, it conveys our humanity.
Water is the very stuff that we are made of. More than 70% of your body is water. Water is the necessary highway that gets all the chemistry going that is your metabolism.
Within Earth's 6 billion people flows 4 billion gallons of water, almost as much as pours over Niagara Falls in 1 hour. The world surrounding us is no less awash in water. It blankets 70% of the Earth's surface, a total of 326 million cubic miles. But of that staggering figure, only 2.5% is fresh water. And most of that amount is locked away in ice caps and glaciers. Just 1% remains to sustain us all. Nature magnifies this sobering reality, distributing our precious supply unevenly, both geographically and over time. The result is that more than 1 billion people lack access to clean drinking water.
Without water, we're dead. It's a very undervalued commodity, and we only know that its value is there when we don't have it. I think Benjamin Franklin said we only know the worth of water when the well is dry.
Where water is plentiful, however, it's risen to new heights as a slickly marketed product. Media stories of tap water laced with pollutants and impurities have convinced millions that the healthier, better tasting choice comes in a bottle. 25% of America's brands are purified municipal water. The majority are drawn from natural springs. What precisely is a spring? Camp Holly Springs in Richmond, Virginia, serving the region since 1923, is an ideal place to clue you in.
This is the surface expression of Camp Holly Springs. This is very similar to probably 99% of the springs that people actually see. What happens is that precipitation, rainfall, is falling to the highlands behind us. It moves through the soil into the underlying aquifer and becomes groundwater. Now, 2-3 years later, it is discharged.
The crucial spot where the water actually breaks through the surface lies farther uphill, sealed in an enclosure called the spring house.
The main purpose between the spring house and containing the spring is to keep any sort of surface contaminants out of the spring, the groundwater itself. It keeps surface water out through rain or runoff. It keeps people from being able to introduce contaminants, because really the water never sees the light of day before it's put into that bottle.
Camp Holly's owners don't pump the water directly from the aquifer. Gravity carries the water from the seepage point through a pipe to a pump house. Such a method avoids any possibility of disturbing the spring's natural flow.
The water enters through this pipe and flows under its own power to our holding tank, which has a capacity of 500 gallons. From the holding tank, we pump through a quarter-mile pipeline to our production facility using a 7.5 horsepower pump. When we're not pumping to the production facility, you can see the overflow pipe and the natural flow of the spring. At this point, we have pristine water with 32 parts per million total dissolved solids.
Outside the company's production facility, the spring water collects in a 14,000-gallon tank. From there, pumps convey it to the top of a 47-foot tower to begin a sterilization process using ozone. Ozone, an unstable form of oxygen, is a powerful oxidizing agent that destroys any microorganism it may contact.
As the water descends from the top of the ozone mixing column, we inject a mixture of ozone gas and water at the base of the column. The ozone being a gas, it tries to ascend the column as the water is descending. This creates a mixture of the two for contact time of over 9 minutes. The ozone sterilizes the water. From this point, the water enters the production facility into our filler to fill bottles.
Part of bottled spring water's allure is that no two springs, or the waters drawn from them, are exactly alike. A spring with an entirely different surface expression than Camp Holly's lies in picturesque Iceland. The water in this pristine lake percolates up from an aquifer reaching depths of a half-mile. The water begins as rain in the mountains of Iceland, which trickles down beneath the ground into layers of volcanic rock.
This country, Iceland, is drifting apart by approximately 2.5 centimeters, 1 inch a year. And this gradually breaks up the lava layers, and this makes it possible for the water to travel through.
The lava rock acts as a natural filtration system for the water before it settles in the aquifer. From there, pumps carry it to the production facility of Iceland Spring, which bottles more than 2 million gallons every year. That's a modest amount compared to the output of major industry players like DS Waters. It operates one of its 28 plants in Sacramento, California. Every day, trucks complete a 2-hour drive to deliver water pumped from a protected spring in the Sierra Nevada mountains. The water, like that at Camp Holly Springs and Iceland Spring, undergoes thorough filtration and disinfection. But the plant's most intensive purification techniques are reserved for the second type of water processed here: Sacramento's municipal supply. Its journey is more rigorous, passing first through a phalanx of sand and charcoal filters. The most crucial filter of all lies further down the line, which uses a process called reverse osmosis. A pump forces the water under high pressure through a vessel encasing a semi-permeable membrane. The membrane consists of multiple layers that act as a very fine filter featuring molecular-sized pores. The membrane traps contaminants and debris from the municipal water supply that are too large to penetrate. But the water molecules are small enough to fit through and flow into the membrane's core.
The municipal water supply that we have in this location is 100 parts per million, total dissolved solids. And through reverse osmosis, we're able to reduce that to 1 part per million. The step following reverse osmosis is to add minerals back in for taste. Purified water can have a kind of a rough taste across your tongue. And when we add minerals back in, we ensure that we have a pleasant tasting product for our customers.
The water then undergoes 2 final disinfection processes. First, it's bathed in ultraviolet light and then subjected to an ozone treatment. Finally, it's off to the filling station. A large part of bottled water's appeal is that consumers deem it fashionable. But eons ago, the basic idea sprang from a matter of sheer necessity.
Early man realized that water was something we need, but it isn't always where we need it. So they learned quickly to be able to transport it, and putting it into vessels was the easiest way to bring it to places where it didn't exist.
The first things that were used to bottle water were things like animal bladders and hollowed out gourds. There are many people who think that ceramic pottery came initially from the need to store water reliably in arid situations.
Civilizations, including Greece and Rome, took water management a step further, engineering monumental ways to transport water from distant rivers. The Roman aqueducts delivered millions of gallons of fresh water daily to the imperial capital. But delivering water was one thing. Keeping it clean was another. In the 5th century, after Rome's fall, innovators in Venice devised an ingenious way to filter rainwater stored in the city's wells. Workers placed a perforated cistern in a conical hole about 10 feet deep. They filled the space surrounding it with fine sand. Sloped stone surfaces channeled the rainwater into the sand, where it flowed into the cistern through the holes near its base. Most of the water resided not in the cistern, but in the sand, which continuously trapped particle debris and microorganisms.
Every time you withdrew water, it was effectively filtered through the sand. And that was the epitome of water treatment technology in Western Europe.
But over the next millennia, the Venetians' example failed to catch on. And as Europe's population exploded, the quality of its water plummeted. In growing urban centers, waste and sewage fouled its taste and poisoned its purity.
It was very unfashionable to drink water. The only people who would drink water were people who had absolutely no other choice. What they would do is they drank beer, and they drank what they called small beer, which was beer that had been watered down to an ethanol concentration of 1% to 2%. That was sufficient to depress the growth of fecal bacteria, which are dangerous to humans. But at the same time, it wouldn't dehydrate you.
Europeans shunned water for the next 400 years. Then, in the 18th and 19th centuries, the rich rediscovered its healthful benefits in the pristine springs far from the cities. Water became not only acceptable, but chic.
What ultimately happened was that people would know of a spring, and then they want to continue drinking that spring at home. And that really is how the bottled water business started.
European water bottlers prospered. The wave eventually hit America. In 1855, New York's Saratoga Springs churned out 50 million bottles. City dwellers, weary of impure municipal water, plunked down the modern equivalent of more than $30 to purchase a single pint.
By about 1900, bottled water industry in America was a big business. In 1913, something happened that changed all of that. In Philadelphia, engineers who had been tinkering with this for years finally came up with a method of adding liquid chlorine to water, which would at least partially disinfect it and essentially make it entirely safe to drink. And so one of the very large reasons for buying bottled water disappeared overnight. The bottled water industry in America collapsed and almost disappeared altogether.
America's bottled brands confined themselves largely to office water coolers for the next 6 decades. But in the late 70s, slickly marketed brands from Europe revived America's love of the product, opening the floodgates for an industry now worth $10 billion. While many consumers embrace water as nature's ultimate beverage, it enjoys another identity as nature's definitive oddball. America's top-selling bottled waters are Pepsi's Aquafina and Coca-Cola's Dasani. Each is purified water drawn not from springs, but municipal water supplies. Water will return on Modern Marvels. We now return to water on Modern Marvels. We think of water as an ordinary substance, but it's anything but. The surprising truth is that this abundant compound doesn't behave the way most substances do. And its chemical and physical oddities are the key to its role as the matrix of life. We think nothing of the fact that ice floats on the surface of water. That happens because water expands when it freezes, increasing its volume by 9% and becoming less dense. This is just one of water's properties that sets it apart as an oddball.
Most substances, unlike water, are much more dense in their solid form than in their liquid form. Glacial acetic acid is an example of that. Here we have a sample of its solid form, and in these beakers we have a sample of its liquid form. As you can see, solid glacial acetic acid acts very differently than water does.
Yes, this is how so-called normal compounds behave. And if water wasn't such a rebel, the consequences would be catastrophic.
If water behaved like most substances, if frozen water were more dense than liquid water, then every year when a pond froze over, it wouldn't freeze over, it would freeze under. And the ice would sink to the bottom of the pond and then build its way up from the bottom to the top instead of from the top to the bottom. All the life in that pond would die because it wouldn't have any liquid water available to it. Nothing could survive. So the fact that ice is less dense than liquid water enables life to carry on even when temperatures shift and get cold during the winter.
What's responsible for water's wackiness? At the molecular level, it's electrically lopsided. The H2O molecule looks like Mickey Mouse ears, with a slightly negative charge near the oxygen atom and a slightly positive charge near the hydrogen atoms.
Hardly anything has this great big negatively charged atom with these two little tiny positively charged atoms. It's what we call polar. It aligns itself in certain ways.
When two water molecules are going toward each other, they have to orient themselves so the positive portion of one water molecule is pointing toward the negative portion of another water molecule. This attractive force between the two molecules is what we call the hydrogen bond. And it's the hydrogen bond that gives water all of its unusual properties.
The hydrogen bond compels water molecules to grab onto one another, accounting for another of water's curious attributes.
Steel is more dense than water, so we wouldn't expect anything made of steel to float. We would in fact expect it to sink, like this steel paperclip. However, if we very carefully take our paperclip and place it just on the surface of the water, we'll find that it will float. You'll notice the subtle indentations that the paperclip is making in the surface of the water. This is because water's high surface tension allows the surface to act as if it were a skin.
We see water's high surface tension in action whenever we overfill a glass. The molecules cling so tenaciously to each other that the water can rise significantly over the brim. Water surface tension explains how some insects can walk atop ponds and lakes. It gives raindrops such a thick skin that they fall like bullets, whittling away mountains over geologic time. And it enhances water's ability to ascend through the capillary systems of plants and trees.
If water didn't have the fabulous surface tension property that it has, trees would be little stubby things, plants would be shorter, the very surface of the earth would look completely different.
Water's single most significant feature, perhaps, is that practically anything except oil dissolves in it. Biologists theorize that water's role as the universal solvent enabled life to begin in the watery cauldron of our oceans.
If you think about what is required to get the complexity necessary to evolve into life, you have to think about how many tries you could have. Tries meaning what ways could you combine molecules or even atoms to make molecules that might yield more complexity and evolve into life. And water is a perfect solvent for that to happen. The water has its polarity, which can align the bits in different attempts to arrange them in such a way that they'll chemically react with one another. And you can do it in an unlimited number of tries because it allows things to move around in all kinds of direction.
Amidst the countless molecules of water making life itself possible, roam scattered misfits, even more peculiar than the rest. 1 in every 6,600 water molecules has hydrogen atoms that are heavier than normal. In a normal water molecule, the hydrogen atom's nucleus consists of a single proton. The heavy hydrogen atom, called deuterium, also contains a neutron in its nucleus. The result is a compound called deuterium oxide, also known as heavy water. Heavy water has special properties tailor-made for nuclear power generation. It's enabled engineers to design reactors that create fission using natural instead of enriched uranium, which is both difficult and prohibitively expensive to produce. Canada's Bruce Power Facility, about 220 miles northwest of Toronto, extracts its heavy water from neighboring Lake Huron. 2,000 tons of the lake's water yields only 2 ounces of deuterium oxide.
The U.S. reactors use light water, but they have to have the enriched uranium to cause the fission. We've gone the other way. The Canadian design is the natural uranium with a heavy water moderator that allows the fission to happen.
In the reactor, 68 tons of heavy water surround cylinders containing the natural uranium fuel. In conventional water, most of the neutrons emitting from the uranium would be absorbed by the water molecules. But the heavy water repels nearly all of them, making them ricochet between the water molecules. This slows the neutrons, redirects many of them back through the uranium, and enables the chain reaction to be sustained.
And this is what releases the heat and causes the water to heat up, which we carry off to the boilers to make steam, which eventually turns the turbines to make electricity.
Heavy water may be a misfit plucked from an oddball substance, but without it, millions of Canadians would be totally in the dark. As it continues to energize a nation, water's standard variety endures as the lifeblood of the world's agriculture. The speed of sound in water is roughly 4,500 feet per second, 5 times faster than its speed in the air, helping enable whales to communicate over distances of hundreds of miles. Water will return on Modern Marvels. We now return to water on Modern Marvels. Welcome to Nebraska, the heart of America's breadbasket. Here, farmers rely on a bounty of water to feed their thirsty crops, and in turn, a hungry world. Agriculture on this scale demands a larger, more consistently available volume of water than the unpredictable rains can deliver. So the state's growers sustain their fields using the time-honored art of irrigation. farmers irrigate 50 million acres of farmland in the United States, swallowing up nearly 40% of America's water. And in Nebraska, the principal source of that water lies trapped beneath the Earth's surface. A vast subterranean reservoir called the Ogallala Aquifer stretches from South Dakota to New Mexico. Over the eons, rainwater has percolated downward, saturating the spaces between soil and rocks, and penetrating porous formations of sand, silt, and clay. Like a titanic sponge, the aquifer holds nearly 1 quadrillion gallons of water, enough to cover the continental United States to a depth of 16 inches. Every year, farmers pump about 5 trillion gallons from wells to irrigate what nature by herself could never sustain. These monstrous watering wands on wheels extending from the wells have become signature features of the Great Plains. They're aptly called center pivots.
As the name would imply, a center pivot, it has a fixed point that it rotates around. And from the air, it gives you a circular pattern that people may have seen when they're flying across the United States or even other parts of the world.
It goes around typically in a clockwise direction, working just like a watch hand and going around very slowly and applying the water evenly over the entire field as it moves. The machine itself is powered by small electric motors at each drive unit or each tower. They consume less than 1 horsepower each.
A center pivot covering 130 acres typically takes 3 days to complete 1 rotation. It can sprinkle 1,000 gallons every minute, enough to fill an Olympic-sized pool in 1 hour. This model, watering a sod farm outside of Omaha, epitomizes a crucial element of every center pivot's engineering: keeping the linked spans of its lengthy pipeline properly aligned as they move.
The very last set of wheels, which is at the outer end, is the master. As that last set of towers or drive unit moves ahead, it creates an angle difference at a flex joint above each set of tires. In the tower box are the switches which sense the angle, and as the angle changes, a switch is tripped, which will energize this motor, and this drive unit will move forward. It will move until it's back in line again, and then it will stop. And this cycle will continue to repeat itself as the center pivot moves around the field.
Center pivots have revolutionized productivity by distributing water more efficiently than any other form of irrigation. One of the older methods it's eclipsed, called gravity irrigation, conveys water through furrows dug between rows of crops. It's still used on about 60% of America's irrigated cropland.
For gravity irrigation, the first thing we need is a water source, and the water source we're using here today is out of a local river. What we typically do here is we lower our basket into the river, and once we have that down into the river, then we're ready to start this 45 horsepower diesel engine that will deliver the water to our gated pipe at the rate of about 1,200 gallons a minute. This field is about 1,200 feet long or a quarter of a mile. We keep the pipe at the top end of the field so that we can run water down the slope to the bottom end to make the gravity system work. The main advantage or reason that we're using this system here is we have an odd-shaped field that's small, that's not very conducive to a center pivot system. Our disadvantages here with this system are we're over-applying water to the extent of about twice as much as we need on the top end of the field to get water to the bottom end of the field.
The roots of this simple form of irrigation can be traced back 6,000 years to Mesopotamia in present-day Iraq. In the millennia that followed, farmers in arid regions around the globe have used gravity irrigation to power the progress of their societies. By the 19th and early 20th centuries, it was enhancing productivity on America's Great Plains. But many homesteaders remained at the mercy of the fickle rains. Just beneath the settlers' feet, the vast ocean of the Ogallala beckoned. But their only means of pumping it to the surface were their underpowered windmills. They could tap just the shallowest groundwater, enough only to water a few trees or fill a bathtub on a Saturday night. The 1920s witnessed unusually generous rains. But in 1931, the skies abruptly dried up. The decade-long Dust Bowl epitomized the grim truth that wherever water vanishes, human misery follows. Winds whipped the dry topsoil away, and with it, the fortunes and dreams of thousands. In 1939, the skies finally opened. But only an effective new system of irrigation could provide farmers the consistent volume of water they needed so desperately. In 1948, a Colorado farmer named Frank Zyback finally delivered. He devised a primitive prototype of the world's first center pivot.
The pipeline was only about knee-high. The towers were made kind of like a bridge to support with cables, and the wheels weren't very big, and the ground clearance wasn't much, but he knew he had a good idea.
Nebraska's Valmont Industries, which acquired Zyback's manufacturing rights in 1954, cranks out an average of 7,000 center pivots each year. Valmont and other manufacturers have produced about 400,000 pivots, now delivering life-giving water to more than 100 nations. They've left their signature circles from Brazil to Saudi Arabia. But in Nebraska, where pivots dominate the landscape like nowhere else, some experts have grave concerns. The 5 trillion gallons pumped yearly from the Ogallala aquifer far exceed the amount nature is able to replenish.
There are a number of locations in Nebraska where the water table itself has been lowered by 30 or 40 vertical feet. And it is a worry to many people. Those are the areas where we've seen a lot more stringent regulations go into effect, where government doesn't allow new wells to be constructed.
Opinions vary, but some believe that only a fifth of the Ogallala's precious water may remain by 2020. But as water continues to sustain a thirsty world, it also enjoys a splashier role as a flamboyant entertainer. During transpiration, the process in which plants release water to the atmosphere, an acre of corn gives off 4,000 gallons every day. Water will return on Modern Marvels. We now return to water on Modern Marvels. Our attraction to water isn't based solely on our instinct for survival. Beyond its life-sustaining essence lies a fluid purity to which we naturally bond. Fountains have adorned civilization since the days of antiquity, showcasing water as a unique artistic medium. One of the most impressive of all spans 8 acres fronting the Bellagio Hotel in Las Vegas. The fountains of Bellagio have gained global renown as a triumph of modern engineering and aesthetics. This eye-popping wonder is the handiwork of water specialists at Wet Design in Southern California.
The fun thing about working with water as a medium is it is the most common, taken for granted element on the planet. And so to coax something new out of it, a different nuance, even maybe an emotion, really gets people's attention.
Wet Design has been producing custom fountains and other unique water features since 1983. These colorful fluid arcs are called laminar streams. Channeling the water through a special sharp-edged orifice redirects its normally haphazard flow of molecules into parallel paths that eliminate all turbulence. And water's surface tension helps hold the streams together.
And you notice that it creates a rod of water that almost doesn't look like water, it looks like a glass or a plastic rod. But you'll notice that it is actually water. We can adjust the flow and bring these streams together and create what we call laminar sparks. Now what we're doing is lighting the water with a fiber optic illuminator that has color in it. Those colors mix, because it's a liquid medium, they mix instantaneously, so you'll get a color mixture. If you pay attention to the colors that you're actually using, if you had a red and a blue, for instance, you would get a perfect purple there as a mix.
Water impresses as it shines and sparks, but we seem to love it most when it dances. At the Bellagio, hundreds of jets called shooters propel plumes of water skyward in artful synchronization to music. The smallest variety are called nano shooters.
And just to show you how simple in concept this is, this little thing here is a valve. It turns on and off when it gets a small electrical signal, just like a battery signal. And it has a little, when it's installed, a little tube of compressed air coming to it. And it squirts that air into this little opening here, and that shoots up. And whatever water, now you got to understand, the water level is sitting about right here. This tube's filled with water, and spurt, up it goes.
One size up from Wet Design's nano shooter is the mini shooter.
This is a mini shooter. Generally the water level sits about right here, and it has an air tank that holds about 5 gallons of air and a water vessel that holds about 5 gallons of water. There's a valve in between them, so when you open the valve it allows the air to push the water out. Generally this thing will shoot up to about 150 feet.
That pop you hear results from a sudden velocity change as the fast-moving pressurized air exits just after the slower-moving water.
This is a super shooter. It's about 10 times the volume of a mini shooter in its water and its pressure. And this shoots about 250 feet into the air.
A different breed of device creates the Bellagio's more delicate water expressions. Gyrating beneath the water's surface are more than 200 robotic pumps, called oarsmen.
Regardless of size, and this is a model of a very small one, all of our oarsmen, underwater robots, have multiple axes of movement. This way, and when you combine those, of course, you get an entire hemisphere of motion. And on top of that, as you change the water pressure, you get what we call the Z movement, up and down.
The Bellagio's oarsmen and shooters owe their timing and grace to Wet Design's computer specialists. Like choreographers of a Broadway musical, they program every move the water makes.
Basically what I want to show here is that now you have two chases going from one end of the lake all the way to the other end. And let's say I don't like that and I want something more dramatic than that. I want the chases to begin from either end of the lake and converge right on the center. I highlight the necessary code and I just basically replace that chase with the one that I'm interested in. So as you can see, we're getting to that part. The chase starts from either end, and now converges towards the center, and it peaks right where the center ring shoots out. And this was done in a matter of like a minute.
Given the spotlight, water compels us to drink in its beauty. "700 million miles from Las Vegas, water is putting on an even more impressive show. And it may be the smoking gun to life on the far edge of our solar system." At any given time, the fountains of Bellagio can propel up to 17,000 gallons of water into the air. Water will return on Modern Marvels. We now return to water on Modern Marvels. In its quest to find life among the stars, NASA has devised a simple strategy: follow the water. On July 7, 2003, it put that maxim to the test, dispatching its probe Opportunity on a 7-month voyage to Mars. In 2002, NASA's probes had confirmed the long-held belief that the Martian poles contained a vast quantity of frozen water. Following its landing, Opportunity would make a discovery that would redefine our knowledge of the Red Planet. Its zone of exploration was called Meridiani Planum, near the Martian equator.
When Opportunity opened up, the first thing we saw was outcrop. What an outcrop is a piece of rock that's been there for a long periods of time and actually tells a history of the region. We have a microscopic imager on board. And we started noticing a pattern in the materials.
The size of the ripples and the shapes of those ripple marks are comparable to ripples in sandstones on Earth that we know are laid down in rivers or in lakes. And so our initial interpretation was that there'd been some shallow sea sloshing the water around, maybe 3 to 6 to 10 feet deep at its deepest, and it could have been spread over the whole area. It could have been the size of Oklahoma.
Opportunity's find is the strongest evidence yet that Mars once had a habitable environment. And other tantalizing possibilities remain.
Now that we've seen evidence of at least past liquid water on the surface of Mars, we have to ask ourselves, is there any liquid water now on the surface of Mars or just beneath its surface? Because if there's liquid water anywhere just below the surface of Mars, there could be microbes in that liquid water, or microbes using nearby liquid water to carry on a life, just the way microbes can live in rocks and in sediment on the Earth.
In 2006, NASA's Cassini spacecraft made yet another enticing discovery of water. Sweeping past Saturn, it detected a spectacular phenomenon occurring on one of the ringed planet's 47 moons, Enceladus. Near the moon's southern pole, geysers are spewing enormous vapor plumes up to 260 miles into space. Scientists surmise that liquid water boiling beneath the surface is expanding and forcing its way to the surface.
If that geyser were to contain liquid water, it would present a real mystery. It's too cold at Enceladus to be liquid. So what's happening inside that little moon to make liquid be possible?
Mysteries aside, scientists believe that Enceladus's water, heat, and organic compounds combine to make it a prime candidate to support life. At the edge of the solar system, or the tip of our tongues, water beckons. Nothing else offers more profound promise or greater wonders.